like to thank Professor Julie MacPherson for coming on today to give us a talk in our webinar series. So I haven't really met you in person too often, but it's nice. I've followed your work, and I've actually met a few of your students at a lot of the Electrochem conferences. So so it's a real pleasure to have you here today, and over to you now, and thanks for giving the talk.
Okay, thanks, Michael. So this is actually a first for me. This is my first Zoom talk, so it's kind of quite strange. I really like to be in front of people and giving an in-person lecture, but we'll see how this goes. Okay, so please bear with me. So I thought what I'd talk about a bit today is some of the work that I do on metal electronucleation and growth, and some of our use of the high-end electron microscopes in order to study this. Metal electrodeposition is really quite important in terms of a tool in order to make nanostructures. Why do we want to make nanostructures, in particular metal or alloy nanostructures, things like nanoparticles, nanowires? It's because in many of the energy conversion techniques or the storage techniques, these types of structures are incredibly important. Now, it's really interesting actually that although I'm going to show you that electrochemistry in general is a low-cost procedure, you know, the reagents aren't that expensive, you can have a lot of control over the process. Most of the commercial applications that are using nanostructures supported onto electrode surfaces in these like energy conversion technologies aren't using electrodeposition. I think there's a couple of examples in the battery field, and I think this is a shame, and I sort of think that we should be moving more to using electrodeposition in this way. And what I'm trying to do in this talk is maybe talk about why it hasn't been used as much as it potentially it could do, and that requires us to really understand more about the mechanism of metal nucleation in order to try and tame and control it. What's nice in electrodeposition, and although you could say in some respects it is a caveat because it's almost got too many variables, is you have a whole host of different parameters here that you can control to tune the structure that you get. And we've played around with pretty much all of them. So you'll have an electrode substrate, the surface energy of which will dictate as well whether you form nanoparticles or you'll form thin films over the surface. We're going to be working with carbon surfaces here, so low energy substrates. You've got potential as a variable, time. I'm going to talk a bit towards the end of the talk, some of the interests that we've been doing in solvent electrolyte and temperature and pH. So if you look at catalysts and support materials that are used today, traditionally, you're going to be looking at sp2 bonded carbon. So most of the catalysts, if we're looking at nanoparticles, are placed on top of this material. And the reason is because this is, you know, sp2 carbons, they do have fairly low background currents, but the biggest probable advantage is their low cost, and they can be made in very high volume. I mean, for fuel cell chemistry, you're looking at needing to produce tons of this. However, there are some potential problems of using the sp2 carbons, and that's been well documented in the literature, which is things like carbon corrosion when you go to elevated temperatures, and then you start to get loss of catalyst material. For those of you that know me, I've been working with boron doped diamond for many, many years now as an electrode material. And boron doped diamond has many advantages, actually. It really does give you a very low capacitance. You get beautiful electrochemical cyclovoltammograms and responses. It has a wide solvent window in aqueous solution because electrocatalytic processes are really slowed down on boron doped diamond. And if you get very high quality BDD, you can actually really push out that oxygen reduction wave so that to a point where you can't even really see it in the aqueous solvent window. I think what's also important is it's significantly more corrosion resistant than an sp2 carbon. So for applications where corrosion resistivity is really important, and a lot of these fuel cell applications, this is the case, this is an interesting material. The problem is, you know, that could be precluding its entry into the market space is the cost. Most BDD is grown using chemical vapor deposition techniques, and it would never be cost effective to do that at high volume. So one of the things we've been working on, and I won't talk about this here, is actually this is Georgia Wood, one of my PhD students. We've been basically looking to produce diamond via an alternative, which is cheaper route, which is high pressure, high temperature. So you produce these kind of microparticles of BDD, which themselves are particulates which behave as almost the CVD material. This material can be milled further. So this is an interesting material because it potentially opens up a route to produce high volume BDD. And it's actually really challenging to get enough boron in using this mechanism of growth so that you can go into the metallic regime, which is what we need to make the boron doped diamond for an electrode process. However, I digress. So if we're looking at trying to kind of tame electrodeposition as a word, we need to try and look at understanding the growth of it and the nucleation mechanisms of metals on electrode surfaces. And as I said, I'm going to be talking about carbon surfaces. I'm sure I've not done justice to the full range of people who've really studied this both atomistically, classically, and come up with many theories over the years. In essence, it boils down to the fact that we take an ion in solution, we directly reduce that ion to produce a metal. We need to produce a nuclei that's of a sufficient size to be stable. So you may get redissolution, movement events on the surface. Once it's stable, you can look at having incorporation of the metal atoms into that stable structure and growth of a crystalline surface, be that a nanoparticle. And terms such as instantaneous and progressive were coined to perhaps describe different sort of regimes of metal nucleation deposition. Although, you know, those terms now are being used with caution. So I would say that a lot of the theories actually for longer term nucleation probably fit pretty well actually. The challenge becomes when you start to look at the shorter terms and are some of these pictures truly describing everything that's happened. And so this is where probably about 10 years ago, John Osteros in Belgium started some really nice work, starting to try and look at early stages of electrodeposition to try and understand the mechanism of growth. And what he did is he started to really use TEM, very high resolution TEM, 3D tomography TEM, to study the structures of the particles that were being formed on the surface. And what John was postulating is that actually in more traditional theories, you might say that once you've got a stable nuclei, that actually you just start to grow on top of that nucleus and you get this crystallization. John was saying that these nuclei actually will move around and they'll actually form aggregates. So you can see here, and these aggregates with time may end up coalescing into a crystallized particle or actually, depending on the timescale, just stay in this aggregate form. And so this sort of electrochemical aggregative growth mechanism hadn't been really postulated before, but you're seeing this prominence of it now being described in the literature. And this was really interesting to us, this short-term nucleation and also John's use of TEM in this way. We'd ourselves looked at atomic force microscopy images of metal nanoparticles, and this is a study we did on platinum, and we were looking at electro-oxidation of an alcohol. It's work by Hussein, and the AFM shows smaller particles here, larger particles here. These smaller particles were more active, catalytically active to the oxidation process. And you could argue, well, it's because they're smaller. But actually when Haytham transferred these particles off the support, so we had to move them off carefully onto the TEM grid and looked at them in TEM, actually you start to see structures here that are very reminiscent of what John's showing. And actually the only difference between the deposition conditions for these two images is we use the same overpotential, we use the same time. This is platinum. It was one at room temperature and one was at an elevated temperature of about 70 degrees C. But clearly the agglomeration of these structures was incredibly different. So this really got me and the people at Warwick who are working on this excited about really using TEM to provide more information. So rather than in that experiment you've seen is looking very much at a static process where we'd deposited the nanoparticle and take it off the surface and then go and look at it. You know, there's a big push in electrochemistry, and I think it's right, is to look at in operando or in situ measurements. And In the TEM world, I'm sure many of you are aware of in situ TEM measurements, especially where people are now putting electrodes into the system and they're monitoring electrochemical processes. So this is being done in metal nucleation and growth and in energy conversion type techniques. So this is a powerful technique. In terms of resolution, I would say it's not quite there to get to your single atom. This is the, if you look at the in situ TEM images, you'll see that you can't see isolated single atoms. People are working very much in this area, but obviously we're putting this high intensity electron beam through an electrolyte. So we have to worry about what that process is doing itself. And in fact, people have used this process to actually induce growth of nanoparticles in solution. And then bubble formation and evaporation of the solution can be a real killer actually experimentally when you're doing this. But it's really interesting. I want you to introduce you to another kind of technique, which is not as well known as perhaps the in situ electrochemical TEM. And this is a technique called identical location TEM. And what it does is it's an attempt to get to dynamic information, but while still retaining extremely high resolution of the best TEMs out there on the market, the aberration corrected. So this term was coined by Microscopy, and it's a kind of time stamping. So it's a stop, start technique. So what you do is you will take your grid, and people tend to use the grid finders. So you can look in a particular location, you do your deposition, you remove from solution, you put it into your highest resolution TEM. So you're now operating under vacuum conditions, you image, and then you go back and you look in exactly the same place and you image under exactly the same conditions. And you keep repeating that process in order to get these timestamp dynamic information time shots. So this is an example of a study by Hector Brunner from Cornell. He was looking at platinum nanoparticles on carbon supports, these sp2 carbon supports. And after cycling under fuel cell conditions, he was showing that there was a agglomeration, a movement of the catalyst nanoparticles. And this is something we're interested in as well, this idea that you can design the most perfect catalyst, but what happens to it in the real environment. So a lot of my work is very much geared to commercialization or real application. So this is identical location TEM. You can do this on the carbon films as I've shown you. TEM grids, they're so thin. It's like a film of glassy carbon that's floated onto the surface. So people are using these as electrodes. It is difficult though to work with them. And for identical location TEM, you have to put in, take out, put in, take out. So you need to be careful you don't contaminate in any way or you damage the film. They can rip and tear. And sometimes you can, they're not as robust as potentially you would like. This, I don't think this is going to play unfortunately, but this video would have shown you these two gold nanoparticles actually under the influence of the electron beam coming together on an sp2 grid, and you would have seen a big hole opening up in the background. So what we decided to do, because a lot of our work was in the area of boron doped diamond anyway, is we needed to try and be able to do direct electrochemistry on electron beam transparent boron doped diamonds so we could put it in the TEM. Now these grids don't exist, so we've had to go and work out how to make them, and this is our attempt. We're looking at other ways to sort of advance our technology, but we think that BDD for use as a TEM support, so it's electrochemically conductive, which is great, so we can use it as the electrode support, but it has a really high thermal conductivity. So when we start to irradiate structures with the electron beam, the thermal energy from that should dissipate very quickly through the BDD. It's very stable actually, even when it's thin, the way we've got it at the moment, supported. It's got very low backgrounds, and you'll start to see that it's a beautifully crystalline material. So when we do these TEM studies, it's like working with a single crystal. And actually it can tolerate high radiation thresholds. So because it's got a high damage limit. So how do we make them? So we grow by chemical vapor deposition. We have a growth substrate and we grow thick actually. So electron beam transparency, you're really looking at trying to keep your thickness probably below about 100 nanometers. And we might grow thick to 300 microns. So what we do is we pop it off the growth substrate. So the whole thing is freestanding boron doped diamond. and it's polished to a very fine surface finish here, and also would be polished to a very fine surface finish here, and we thin it down effectively. So we take the thick diamond and we thin right down. From polishing, you can probably polish down to about 10 microns, but it's really challenging. You need very experienced, accomplished polishers to do this. We work down to about 50 microns because we want to handle this material as well. So we can handle 50 micron BDD. And then what we do is we thin by an iron polishing technique. So we'll have a region, and we end up going through the BDD in the center to really prove that the regions around the center hole are electron beam transparent. And one of the nice things with TEM is you have the ability to do things like electron energy loss spectroscopy. So you can get spectroscopic information on the metal ion identity, the oxidation state. You can get diffraction information out on very, very high resolution. So we can use, this is an EEL spectrum to calculate the exact thickness of our electron beam transparent diamond. So I said to you that we can get regions thin enough to become a TEM support. And when you look at it, the way our diamond grows is it's actually preferentially oriented with a 110 interface. And so when you do this area electron diffraction onto that BDD, you can see this beautiful kind of like single crystal of 110 surface. And so this is our support structure. What I need to get you to think about though, when you look at the TEM image, is it's really easy to just think of it in 2 dimension, but actually the beam is going all the way through the substrate. So you're going through atom columns, and I'll come back to this later, because this is actually a really nice thing we can do when we look at atom intensity. But you can see that this is a 2-dimensional representation of a 3-dimensional surface. So always bear that in mind, even though it's going to look 2D to you, it's actually a 3-dimensional structure. So we work with our theory colleagues at Warwick in chemistry, and we're looking to now simulate the structure of the BDD, because at the surface it's going to be terminated. Everything we do is on oxygen terminated diamond. It's a very stable form of termination. We don't use hydrogen termination for these studies. And to start off with, what we decided to do is look at initial stages of gold electrodeposition. Golds are quite a simple metal system to deposit, hydrolyzes nicely, but we really wanted to look at what's going to happen at these initial stages using this concept of identical locations, so that we can go back to the same area each time. And our locator points are actually, when we cut a hole in that diamond, it has a very unique structure. And actually it was surprisingly easy to go back, much easier than we and our electron microscopist colleagues found, to go back to exactly the same area. So we dip our BDD grid into the solution. We can record electrodeposition CVs, and we can decide what potential we want to hold at for what time. For all the studies I'm going to describe, we use high overpotentials in order to create very small, presumably stable nuclei and a high density of nuclei. So let me show you what we do. So I'm just putting up a picture here of Hatham, because he's been instrumental in driving all of the work that we've done on metal deposition on these TEM substrates. So this is a 5 millisecond deposition. And you can actually see here, we can, depending on the angle that we image at or the focus that we have, you can focus just more onto the BDD itself, or you can focus onto the gold. Here you can actually see really nicely, so this is the aberration corrected transmission electron microscope, the atomic resolution of the BDD background. But you can also start to see, after 5 milliseconds deposition, you can see these single atoms on the surface. Not only do we see single atoms, but we also see evidence of what we've called atom clusters. They're atoms that have come together, but they've not formed themselves into a crystalline structure. And this is another example of these atoms here. But as I said, please remember, you're not looking at a 2-dimensional image. This has a 3-dimensionality to it. And then obviously here we also see, after 5 milliseconds, a nanoparticle. Now, this is one of the issues with TEM and anybody reporting microscopy images, is you get so many structures on the surface. So when you report your data, you have to work really hard to get your statistics to make sure you're giving a faithful representation. And I think this is where things like the machine learning and AI will come in to really help microscopists and the scientists who use it to process that data faster and faster, because there is so much to look at. Okay, so let's sort of show you some examples of what we do. One of the first things we had to do, and this came from our electron microscopy colleagues, was they said, okay, if you're going to be doing this and you're looking for things moving around on a surface, you need to prove to a community that the electron beam is not inducing movement of atoms. Okay, because you can see here, I can now see and deposit single atoms. So if I'm going to move anything around in an electron beam, that's going to be easier to move an atom than it is a nanoparticle. And for these experiments, what you do is you image once, then you go and do your second deposition, then you go and image twice. So you only do one scan and you use the same imaging conditions. And so here what we have is a nanoparticle and we have 41 atoms. And so what we did is we imaged that same area 10 times. So this is effectively like capturing 10 frames of a movie. And we were looking to see what's moving around due to the electron beam. So we're not doing any electrochemistry. This is just looking at electron beam induced movement. And you can see that after 4 frames, there is hardly any movement really of the single atoms. Even after 10 frames, you can see here, so this is imaged twice, this is imaged 10 times. 66% of the atoms on the surface have moved a mean displacement of less than this value. So actually, for us, because we're probably only going to be doing, and actually what limits us is the amount of time we can get on a very expensive microscope, you know, probably a maximum of like 5 sessions, 5 time-stamped images. We can safely say, even at the level of a single atom, under the imaging conditions we're going to use, we're not perturbing atom movement. That means if atoms are moving, it's highly likely to be due to the electrochemical potential that we're applying. Okay, so just to remind you, in this experiment, this is what we do. So we deposit for 5 milliseconds, we take out, we image, we put back in for a further 5 milliseconds, we take out, we image, we put back in for a further 20 milliseconds. So we have time stamping at 5 milliseconds, 10 milliseconds, and 30 milliseconds of the process. And we're looking in exactly the same area. Now, obviously, one of the things we've had to work really hard with is bringing the substrate in and out of solution, as all anybody who's doing identical location, and not getting perturbation of the particles or whatever's on the surface due to how we've handled it. So handling is essential, but handling is essential anyway in anybody doing any form of microscopy. One of the things as well we asked our DFT colleagues to think about for us is, can a single atom, just by virtue of the thermal energy of the system, move around? So we asked the DFT colleagues to look at energy barriers on the surface, because actually in one of our steps in the TM, you actually do a thermal bake. So you slightly elevate the temperature of the system. And again, we wanted to be sure that that temperature elevation wasn't causing an effect on anything we see moving. And so from the DFT simulations that are coming out at the moment, the thermal barriers for atom movement seem to be too high for thermal motion at room temperature to be a concern to us. Okay, so what we've done is we've checked the electron beam isn't going to be moving the atoms, and we believe from the DFT and some follow-up electron microscopy experiments we do that we don't believe the thermal energy of the system is going to move them around. The other thing I want to point out, and I think is really neat of this ability, is if you can measure the intensity of a single atom, that means you can start to count exactly how many atoms are in any of the 3-dimensional structures you see. Right, so when you're imaging with this very high resolution electron beam, you're actually imaging through columns, right? And if you know the intensity of a single atom, you measure the intensity of each one of these atom columns and you report that as a spot effectively. And we can calibrate this and pull out from intensity maps, which is what you're seeing, how many atoms are in there. So if you wanted to, we can now actually convert all of our 2D images, because we have that single atom represented, we can convert it into a 3-dimensional representation, which I think is really neat. The only other way to do that sort of thing in TEM is using tomography techniques, and I'm not sure whether they can get to single atom or not. I'm not sure on that. So again, to remind you, these are sort of images we can get, and you might be misled of these atom clusters thinking that they're just you know, a scatter of atoms. Actually, they've got three-dimensionality connected to them. Okay, so let's sort of have a look at what we see. And again, what we've tried to do is, with all the images we've created for these different timestamps, we've tried to look for emerging patterns across the surface. So as I said, there is just so much data to look at. So what we're doing here is we image the surface after 5 milliseconds of growth, and we pick these 6 zones. Then we did a further 5 milliseconds of growth and looked to see what happened in these zones. And for each one of these zones, we atom counted. And actually, we found in this particular image that in this area, and this is not to say what's going on in other areas, and I'll show you that actually none of these were really growing significantly in atom number. Really, what they were doing was just almost under that potential field, undergoing a rearrangement. Growth was occurring on different places of the surface. So this was interesting to us. However, it gets really interesting when you start to look at more detailed pictures of the surface. So this is an example of a crystalline nanoparticle. Okay, you can see how the atoms are formed into these nice crystalline lines. This is one of our atom clusters, right? So it's got no preferred crystallographic orientation yet. This is at 5 milliseconds. We've counted the number of atoms in here. If we then click to 10 milliseconds, what you see is it still is containing the same number of atoms, but actually it's starting to rearrange itself again. And then after 30 milliseconds, this, in order to become stable, and this here is a crystalline nanoparticle, it's actually lost atoms. So it was interesting because you often think of growth as always things growing inside. But for those of you who considered processes like Oswald ripening, that, you know, things could also be getting smaller in size in order to reach a crystalline state. So this has gone from an amorphous cluster to a single smaller crystalline nanoparticle. So these images here are actually my favorite. Here you have a nanoparticle and you have an amorphous cluster, okay? And you can see these two are quite closely spaced. This is at 5 milliseconds. We've counted the atoms. If you then go to 10 milliseconds, what you can see is that amorphous cluster, it's decided that the way it's going to become stable is actually to just give all of its atoms over to this nanoparticle. And that's how it's basically just disintegrating itself and feeding into that neighboring nanoparticle until that neighboring nanoparticle itself turns into a crystalline nanoparticle. And you start to see a beautiful cleanup of the atoms around that particle. This one also is really, you know, so they are, I mean, when we saw these images, we were really amazed by them. Here you have a single nanoparticle. Here you have 5 amorphous clusters. Question is, can we predict what's going to happen? Are the amorphous clusters going to grow and get bigger? Are they going to disintegrate? So if we follow this after 10 milliseconds of growth, you see that all of those amorphous clusters, and this one's here, disintegrated into this nanoparticle. And this nanoparticle, because it's suddenly got all these these atoms coming onto it, has itself become amorphous. This particle here, it's keeping itself, it's started to go crystalline. It hasn't decided to contribute to making this structure get bigger. And if we follow it with further time, you can now start to see that that amorphous structure is recrystallizing out, okay? And you can see here, our particle 6 stays crystalline. So these are just images here of the collective process of these timestamp locations and showing movement at the single atom level. This one again, you've got a nanoparticle and amorphous cluster. And what was nice is we almost captured this bridge formation between the two. So you've got sort of particle atom transfer between the two states. One of them is going to win out over the other, and you eventually form a combined nanoparticle. So I think these sorts of images were just amazing to us at this level. And we're showing that what's going on at these sort of early times, yes, like John Osteros had said, it's far more complicated than perhaps had first been thought. And so, you know, there's still lots of things here to question. You know, no study is ever perfect. And if anything, this has just thrown up more questions. So what we've seen is this rearrangement of these atom clusters to ultimately form these crystalline nanoparticles. we see that atom clusters can dissemble, but they can sort of feed into existing nanoparticles. And so I like to think of it as a form of like surface mediated Oswald ripening. What's interesting to me is you have all these atom clusters. Some of them sit very close to a nanoparticle, some of them sit isolated. They all have these different geometries and arrangements. Could you ever predict using calculations, looking at thermodynamics of the system, could you ever predict, and the energies of the system, sorry, could you ever predict what that atom cluster is going to do? Because that's really interesting to me, because you can see all these different patterns of behavior. And the other thing that I question is these single atoms that we see. We're always seeing single atoms. Are they pointing defect sites on the surface? Is that why they're sitting there and they're remaining in those positions until we start to put the potential on? Obviously, with the electrodeposition, I said perhaps, I think it's a great technique, but there's almost too many parameters to change. So how will I change them? If I change the metal, I change the carbon surface, the overpotential, all these things. How does that change the picture? And then trying to relate our stages of growth to then how that links into the electrochemical aggregative growth mechanisms. And then always you have to consider in any form of science, how by making the measurement, am I actually influencing the measurement, right? So is there anything I'm doing which means I really need to take that into account in the interpretation, and that needs to be clearly spelled out in literature and papers that we write. The other thing that I just want to sort of go on to for the second part, which is shorter, is the other area we've been working on as well is looking at the role of the solvent. Now, the solvent in electrochemistry, most people tend to use aqueous solutions. But if we change the solvent, we're obviously going to be looking at changing the viscosity of the solvent, the mass transport properties. You'll be able to changing the electron transfer kinetics of the system. You need to think about how that solvent is going to interact with your solute system, which is the metal ion. And then what is particularly interesting to us at the moment is mixed solvent systems. Now, anybody that works with ionic liquids, and Debbie gave a talk recently on ionic liquids in sensors, and deep eutectics, it's really difficult to actually exclude water. So for many of these people, they're actually already working with a mixed solvent system. And so understanding the role of water in the system is really important. Now, I've just pulled out two papers that I've found interesting in this area when we were looking into this. One is in the battery fields. So people have moved here, and this is not the only study, to changing the solvent, changing the electrolyte to see if they can try and inhibit the growth of the dendrites. Okay, because lithium dendrite formation is a big problem in batteries. This paper, actually, I think Michael's on this paper as well, from Giro's group, really kind of made me think about the role of mixed solvents in a bit more detail before we started our studies. And here what they're doing is taking acetonitrile as a majority solvent, and effectively water in there is in the minority. So it's a solute, and looking at water oxidation. And what you have to think about is, and actually I'm now teaching this in year two phys chem, is when you have water in the bulk, it will have a certain structure. When you start to take water and have it as a minority solute in another solvent, it will completely change its structure. And therefore it's going to change its properties because it's changing its bonding. And is this going to influence for us the electrochemistry? So this paper showed that by changing the bonding environment of the water, by having more of the acetonitrile, you could influence the oxidation of the water system. We're also interested in water acetonitrile systems. Okay, so these are miscible systems. So we're not looking at, there's a lot of very nice work that goes on at liquid-liquid interfaces. So you have, these two nicely separated phases. The water and the acetonitrile will mix very nicely together. And we're looking at palladium, and we chose a particular ion. I can talk about this later if anybody asks me why we went for the acetate, but we've got the palladium acetate. And we're going to look at deposition of palladium acetate in water-rich, acetonitrile-rich systems, and start to look at what role this plays. Now, even just by considering this particular ion, palladium acetate, if you think about, you could just write it down as 1 palladium to 2 acetates, and you've got charge neutralization, right? But actually, even the bonding structure of palladium acetate is more complicated than you might think at first look. Now, when you take the palladium acetate and you take a water system, we can do the CV, and all of this is done on boron doped diamond, okay? You do the CV of palladium reduction in a water-based system, you see palladium electrodeposition, and you can see palladium oxidation behavior as well. And when you go and look under a scanning electron microscope, you can see the formation of palladium particles, palladium structures. However, when you do this in pure acetonitrile, you still see reduction behavior. You still see palladium 2+ going to palladium 0, but your oxidation peaks way more shifted out. Plus, you don't see any evidence of the palladium metal itself onto the electrode surface. So this was interesting to us because it was saying, okay, so if we take the palladium acetate in acetonitrile, we cannot do electrodeposition. Okay, so some of you may realize immediately why this is. So we thought we knew why this was, but we thought we really need to prove this as well. And so what we did is we threw a lot of analytical techniques at trying to understand how the water acetonitrile is bonding, but also what's going on with that palladium right in that inner solvation shell. Okay, how is that? What's that palladium bonding to? Because if you want to deposit palladium from the palladium 2+ salt, all those ligands have got to fall off. You've got to be able to have that process happen quite easily. What we did with proton NMR, we did UV-Vis, Raman, infrared, all told us the same story, that when you're in 100% acetonitrile, the acetate ligands want to stay very firmly attached to that palladium. There is no driver for the acetate to come off. Okay, so that means purely when you're doing electrochemistry in the acetonitrile, all you're doing is just changing from the 2+ to the 0 state, but it still remains solvated with its acetate ligands, and we'll just move away from the electrode surface as in a standard sort of non-metal electrodeposition process. However, as you start to put in what we're doing here, small amounts of water, even when we consider just adding 10% of water by volume to a acetonitrile solution, that water loves the acetate. So what happens is the water acetate interaction is stronger. And what it does is it pulls it out of the inner solvation shell, and you start to free up that palladium for bonding to the solvent itself, which is acetonitrile. As you start to increase the water, you move from more of a pure acetonitrile bonding to a mixed acetonitrile water, to when you go to majority water, that palladium is well solvated with water molecules. At any point at this position, from 90% all the way through to 10% here, you can get electrodeposition because I've managed to get off those acetate ligands. So what we were interested then is to start to look at, well, what kind of structures are we going to be forming in these sort of mixed solvent systems? And we looked at a acetonitrile rich. So we've got 90% acetonitrile, 10% water. We looked at a 50-50% volume by volume, and we looked at a water rich. So you had 90% water, 10% acetonitrile, to sort of see how this mixed solvent is actually going to impact on the morphology of the deposits that we saw. We used our electron beam transparent TEM grids because we could get very high resolution. So we could see if we were seeing intrastring phenomena. For these studies, we haven't gone to very, very short times because initially we were just looking for longer time periods to see what we saw in terms of larger scale morphological changes. Okay, so again, I'm using a high overpotential to really drive the nucleation process, so high density of nucleation sites for a much longer time. This is in the acetonitrile rich solution, and what you can see, and this is, you can see the length scales here, these are just different length scale images, is that under these conditions, you're tending to get majority crystalline nanoparticles. The blue and the green arrows just indicate the fact that we have an electron beam transparent grid that's really different to the commercial carbon ones you'll use, where you have a thin glassy carbon floated over either a copper or gold support. so there you don't want the back support to be a problem, right? So you want to try and construct an electrochemical cell where everything's on the front face. We just dip our entire grid because the whole thing's diamond into solution. So you get deposition on both sides of the faces. And you can see this by focusing in and out. So you could focus on one side and then come back and focus on another. So we can tell exactly which particle is on one side and which is on the other. But the majority are predominantly nanoparticles. And you are starting to see what we see, some form of coalescence. So coalescence is different to aggregation. Aggregation is where the particles just come together, but they haven't merged. So imagine in coalescence, they've come together and they've merged to reform a beautiful crystalline structure. But also in the background of all of this, when we zoom in, we've still got single atoms and we've still got atom clusters, but they're very much in the minority. What we're seeing under this length scale is these beautiful nanoparticles emerging. And actually, when you go and look at these high resolution ones, remember the boron doped diamond, because as I said, by the time we've polished it, it's majority 1110. It's like we're doing single crystal electrochemistry or kind of electrochemical microscopy. When we looked with the microscopist at these images, they said it almost looked that there was starting to be evidence of epitaxial growth, that the underlying crystal structure of the BDD was actually influencing the formation of the alignment of the nanoparticle. Okay, if we go to 50-50, what we see is we're still seeing nanoparticles, and we still see in the background, we can see our single atoms, and this allows us to remember to atom count. If we can get a single atom, we can do the intensity, but we're seeing a greater emergence of coalesced structures. So more of these nanoparticles are coming together to form coalescence. And we can start to look at these in higher resolution. Then when we go to the majority water, what we're seeing is the emergence of what we call these kind of fractal-like dendritic nanostructures. So when you have majority water, you seem to have like very much three-dimensional uncontrolled growth, giving you these dendritic structures. But again, you can still, if you look for them, see the single atoms, and you'll see coalescence events, but you just see a larger proportion of this. And so we can represent this in this way. You can see that as you increase up the amount of water, the nanoparticles are becoming less circular, they're increasing in perimeter, and you're getting more of these dendritic type structures are evolving. What we can do then is we can move and go to longer times, and we see very similar events occurring. So we're not doing identical location here, we're just looking at different areas for different mole fractions of water with acetonitrile. And again, organic rich, mostly nanoparticles. The mixture, you see the coalescence events, and then the water rich, you really start to go to this sort of almost like very much fractal dendritic growth. And we can represent this with statistics. So again, statistics is, as I said, is really important with microscopy, that you try and represent as best you can what's going on over a large area of the surface by looking in many different zones. And then this is just, we really let the system grow. I think this is a 300 seconds growth. At this point, everything was too thick to even do transmission electron microscopy on, so we had to resort to scanning. But you can see quite nicely, organic rich to water rich over here. Very different morphology that you're getting. So you can imagine, in things where you don't want dendrites growing in lithium battery chemistry, you can see that just playing with the solvent contribution is completely changing the morphology of what you've got. The question is, why is this? Okay, so if you look in the literature, there is some work done on palladium, but mostly there's a lot done on platinum with acetonitrile and looking at water mixes. It's well reported, especially on platinum. This is a study by Herrero, Juan Feliu and Copa, where they were actually showing that if you look at this reaction and you start to put acetonitrile in, the absorption of the acetonitrile on the surface is starting to play a role in changing the catalysis kinetics. So they were commenting at this point that acetonitrile is absorbing. This paper here as well, is also talking about how absorption of acetonitrile can impact on processes. And actually the orientation of the acetonitrile is also being dictated by the mole fraction of the acetonitrile versus the water. And we think of similar things going on, that the acetonitrile in some way is habit modifying the palladium crystals that we're growing. It's slowing down the growth, whereas in water, it seems to be growing in this three-dimensional structure and going dendritic. But as I said, it's interesting to us. And I think there's a lot of people at the moment starting to get interested in roles of electrolytes, how you manipulate the electrolyte in electrodeposition, as opposed to just playing with the potential or the time characteristics. So as I said, it's an area that's of interest to us too. And then finally, I put this up because actually it sort of shows the power, I think, of taking, so I think most of you online will know my colleague Pat Unwin, and will know that Pat's been, has been the main driver behind development of scanning electrochemical microscopy. And Pat's had a bit of a foray into combining the SECCM with sp2 carbon grids, and has actually looked at a palladium electrodeposition system. And in the palladium electrodeposition Pat looked at, they were, it didn't quote over potential, but I think looking at their CVs, this is a fairly low over potential. They were seeing they can actually just deposit and then go and look in a particular region and see what they've done and correlate the electrochemistry with that region and that microscopy deposit. And in this particular area on the sp2 grid, you can't quite see single atoms, but you can definitely see evidence of these aggregated structures. So this is a much shorter time scale than we're showing you as well. And this is just in water. So it'd be interesting to go longer or even to go shorter, to go to the early stages. But it also flags up like where we could go with this, which is basically taking the BDD-TM grids. You can see the amazing resolution you can get, the real nice contrast against the boron doped diamond background, the ability to very nicely resolve the single atoms to single atom count. And you can imagine with this combinatorial approach, really creating a whole suite of nanostructures across that surface with variations in potential time, electrolyte conditions, that you can really start to go and look and start to profile what's going on in some of these electronucleation and growth mechanisms. So this is an area we're really interested to try and develop. So if anybody out there is really interested to work with us on this, please just drop us a line and we'll see what we can do. Okay, the most important slide. Let's finish the talk now. So hopefully I've just given you some things to think about as well. As I said, when you do research, you can't answer everything. And sometimes by doing research, it throws up more questions than answers, but that's good. And if it's stimulated you to go and think about things that you could do or things you want to go and try, that's great. That's the whole point of doing scientific research. What I'd like to do is thank in particular Haytham Hussain. He's now at Southampton with Phil Bartlett. He's been, as I said, a huge driver in a lot of this work, and has really, spent many hours poring over TEM images, trying to work out what we have that's going on. All our computational work has been done through Raini Mura at Warwick, and I really can't say thank you enough to the electron microscopy and spectroscopy RTP. We have amazing facilities at Warwick, and we shouldn't forget that. And the team there doing a really great job of training the students, allowing them to use the microscopes, really working with us to understand the data. And then there's a very strong team as well at Warwick in the diamond area, as people know, and we work across departments developing the different things. So finally, in terms of commercial people we've worked with on this project, we've worked with Element 6, who grow all our diamond for us, and AstraZeneca, who are interested in metal recovery systems. And thank you for your attention. Hopefully I haven't gone on for too long.
Fantastic, Julie. Amazing presentation. The use of TEM to characterize the nanostructures, I think that's the most comprehensive and talk I've ever seen on it. And it's nice the way you've introduced the difficulties and then the opportunities and how it can be linked to applications. And also, I always love to see biophysics stuff, so that was great. Okay, so maybe if you can just stop sharing your screen, and we can get
okay.
from the crowd.
How do I do that?